My name is Charlotte Peterson, and today I'm going to talk about nanoscale control of competing interactions in a 2D spin ice analogue. I want to start by acknowledging all of the people who I worked on this project with, in particular Alan Farhan from the Advanced Light Source in Berkeley, who did all of the experiments. So artificial spin ice is a lattice of nanomagnets where the arrangement of the nanomagnets can be controlled precisely, and it was designed initially to mimic naturally occurring frustrated systems. A key feature of these magnets is that they're long and thin, which implies that the direction of the magnetic moment can only point in one of two directions, along the long axis of the magnet. And so we can think of it as a spin. The depth of these magnets is also very thin, which means that the energy barrier for the magnetic moment to flip from one direction to the other is on the order of kBt, and that makes the system thermally active. The most exciting part of this experimental system is that the direction of these spins can be imaged directly as a function of time as the system relaxes. Artificial spin ice is named after spin ice, which is an example of a naturally occurring frustrated system. Water ice is another example of a naturally occurring frustrated system. Here in this picture, the white circles are oxygen atoms and the black circles are hydrogen atoms, and in the ground state of water ice, each oxygen atom has two hydrogen atoms which are close to it and two which are far from it. And arrangements that satisfy this rule are said to satisfy the ice rule. So you can imagine that if you have a whole lattice of this water ice, which is a tetrahedral lattice, there are many possible configurations which satisfy this ice rule, having two hydrogens close and two far, which means that there's a large degeneracy of the ground state, which means that water ice has a non-zero entropy at zero temperature. Pyrochlore spin ice is an analogue of this water ice, has the same structure, but now in the corner of each vertex, instead of a hydrogen atom, there's a spin which can point in one of two directions, either into the middle of the tetrahedron or away from it. And the system has the same ice rule, so the lowest energy state has two spins pointing into every vertex and two spins pointing out. So in the blue here, this is all of the ways for one vertex that the ice rule can be obeyed. So each one of these states has two spins pointing in and two spins pointing out. However, if we were to try and map this situation to 2D, the most simple way to do this would be just to arrange the spins in a square. However, here the situation is different. Now, all of these configurations drawn here satisfy the ice rule. However, these two on the left have a lower energy than the ones on the right. And this is because the interaction strength between opposite spins is different than between adjacent spins. And so two of them have a lower energy than the others. And so if we were to construct a whole lattice of nanomagnets like this, it's been found that this actually has an ordered ground state. And so this kind of frustration has been lost. So what we want to do is try and modify the lattice geometry to introduce more competing interactions. So this picture here is the lattice we'll look at. We call it the trident lattice. So it has sets of 3 parallel nanomagnets which meet each other at 4 nanomagnet vertices. And we call these sets of 3 tridents. So if we look at the interactions in the system, we can see that for spins, for the interactions within one trident, the most favorable configuration is to have all of the spins head to tail, so alternating. However, if we look at the interactions between the vertices, again, the lowest energy interaction is head to tail, but we can see that in this geometry, these two arrangements are not compatible with one another, and so this leads to competition. In this work, we'll classify what's happening in our system by classifying the configurations in each vertex, and these are classified by types 1, 2, 3, 4, in increasing energy, and also by classifying the configurations of the tridents labeled here. So to look at the dynamics of the system, we first decided to start from a known state, so when all of the spins are pointing in the same direction, and look at how the system relaxes. So that's what's shown in this output of the experiment. So you can see that initially all of the spins were white. That indicates the direction of the spin. And then as the system relaxes thermally, we can see that some of the directions of the magnetic moment start to flip. So they become black, so they point in the opposite direction. And then we can see that the system seems to be relaxing to some kind of disordered state. We can also look at this relaxation process by classifying the system into the vertex and trident types that I just showed. So that's plotted here for the experiments. So we can see that we started in an ordered state, and then we can watch the relaxation as a function of time. I also simulated this with kinetic Monte Carlo simulations. These plots are shown on the right here, and we can see that we have a good agreement between the simulation and the experiment. We can tune the strength of the competing interactions in the system by changing the lattice parameters. In particular, we can vary V while keeping A constant. On the left here, we've drawn configurations which satisfy the vertex interactions, and on the right, we've drawn configurations which satisfy the trident interactions, and their energies of these building blocks are plotted above as the first band and the second band. The competition is maximized when this delta E is equal to 0. Another way to think about this is to consider the energy of the whole lattice when it's tiled either with the lowest energy trident, trident type A, which is compatible with vertex type 2, or the lowest energy vertex, vertex type 1, which is compatible with trident type B. And you can see that the energy of these two configurations is equal this value of B, which is equal to about 1.5 times the distance A. So we did that in the experiment. So here, this middle picture corresponds to B being equal to 1.5 times A, so when the interactions are balanced. And we can see that as we increase B from left to right, we go from an ordered picture to a disordered looking picture to a different ordered picture. And so we can classify that with our vertex populations and trident populations as before. So the lines here are the simulation and the points are the experiment. To look at lower temperatures, we also did the same experiments, but with smaller nanomagnets. So now here B is again the point where the lattice parameter B is equal to 1.5 times lattice parameter A. And so again, we see we go from an ordered state to a more disordered one to a different ordered state. We can clearly see that in the populations. So for example, if we just look at the population of trident type A here, there's a low population here where the two trident types are balanced to one where it's dominated by trident type A instead of trident type B in the first case. Rather than just looking at the classifications, we can also look at the structure more explicitly. So we do that by calculating the magnetic structure factor. We calculate this directly from our wheel space images. However, this is actually what you'd measure with a neutron scattering experiment, and it probes the correlations in the system. And so we can see that for small values of B, we have an ordered state, which is characterized by sharp peaks. And then we have a diffuse scattering at our critical value of B. And if we increase B further, we see that we again have sharp peaks, but they're in different locations than the initial one. So we have a different ordered structure. We can also compare this to other people's attempts at introducing frustration into these kind of 2D lattices. So one of the other promising ways to do this was to, instead of considering a pure 2D system, was to add a height offset to a square lattice. And so this means that this interaction between opposite nanomagnets can be tuned to have the same strength as the interaction between neighboring nanomagnets. So this has been done before, and this is the structure factor measured. And we can see that it's quite similar to a structure that is just generated theoretically that satisfies the ice rule, and that's its only constraint. To compare that directly to our trident lattice, our lattice has a different geometry, so it's hard to interpret this in the same way. However, our geometry is very close to a square lattice, so we can just map our system onto the geometry of a square lattice and then recalculate the structure factor, which is what I've done here for both the experiment and the simulation. We can see that the behavior is quite similar. In both cases, we see a general diffuse scattering. We don't have kind of the same kind of sharp features in the trident lattice as they see in this theoretical ice rule main structure. So it's not entirely the same. So just to summarize, by looking at this trident lattice, we can have nanoscale control of these competing interactions, and this gives us a disordered state at low energy. And the advantage of this system is that it's experimentally straightforward compared to the one where you have a height offset, so a kind of quasi 3D lattice. This one is entirely 2D. If you have any questions, please feel free to ask. My email is here. Thank you.